Okay, good afternoon, everyone. Welcome to the last lecture in our series on soliton and solitary waves for physics and in physics and mathematics. And the last speaker in the series is Dr. Daniel Sadatman. Daniel was also instrumental in setting up this mini school, so it's right that he can do the grand finale of the school. Yep. Daniel is at the moment a postdoc in Stellenbosch University in the group of Professor Herbert Weigel, but he did his PhD at the University of Mashhad. And afterwards, he spent some time at the Russian Academy of Sciences. And later, he was back in Iran as an assistant professor for a few years. And since a couple of years, he's in Stellenbosch as a postdoc. Yeah, Daniel, please, you're welcome to start your presentation. And at the end of your talk, I think Herbert and Professor Malamet will assist in moderating the questions. Yeah, so Daniel, please, over to you.
Okay, thank you very much for the introduction. And good afternoon, everyone. In this lecture, I'm going to talk about the scattering and collision of solitons in 1+1 dimension. The structure of my talk is as follows. In the first slide, I've just introduced some solitons and solitary waves in the nonlinear Klein-Gordon models. Actually, I specifically introduced the three most important nonlinear Klein-Gordon models, which can be found in many texts. Then I try to show how they scatter from each other in the form of integrable and non-integrable models. And I introduce some examples of environment that such solitons can be created inside such environments. Then I show that how these solitons and solitary waves, when they interact with the PT symmetric perturbation, and I will show their behavior after the interaction. And finally, I show my results when number of solitons collide with each other to see what happened about the maximal energy, density, and elastic strain at the collision points. Let's start with the simple linear Klein-Gordon equation, which is written in this slide, as you can see. The solution of this Klein-Gordon equation are well known. They are in the form of the plane waves. If we have such a solution, we know that if we calculate the phase velocity of the waves, since each part of the waves has a different velocity, when these waves moves in the medium, the velocity cannot. In fact, the velocity cannot be constant, and as a result, when we have two different ways of such a equation, when they interact with each other, of course, they cannot retain the shape after the interaction. But if we add a cubic term to the linear Klein-Gordon equation, we have the form of the nonlinear Klein-Gordon model. In this situation, the nonlinear terms and dispersive properties can balance each other, and we can have a solitary waves in such an equation. In fact, if the soliton of such an equation exists, they must go to the minimum of the potential in plus minus infinity. And when such a solitons moves, their velocity are constant in the medium. If they interact with each other and keep the form after the interaction, we call such waves as solitons. Here, I just want to introduce the three well-known nonlinear Klein-Gordon equations of the Klein-Gordon equations. In this lecture, I specifically talk about the sine-Gordon model. As you can see from here, if the potential of the Lagrangian will be in the form of 1 minus cos phi, we call it the sine-Gordon model. And if the potential will be in this form, we have the phi-4 and phi-6 model. In fact, the name of phi-4 and phi-6 model comes from the power of the potential. As you can see, the equation of motion can be extracted from the by Euler and Lagrange from the Lagrangian. And in this talk, I just want to talk about in three nonlinear Killing-Gordon equations. And the first equation, which is sine-Gordon model, is integrable, and the last three equations are non-integrable, and we will see about the solitons waves of this equation. In fact, we also have a higher order terms of these models. We call it phi-8 and phi-10. And the solution of this model, of course, this solution does not have any analytical soliton solution, but we can solve them numerically. There are two famous books in this model for the sine-Gordon and phi-4 model. As you can see here, the sine-Gordon model and its application, and another book is the dynamical perspective on the phi-4 model. I think our last three speakers wrote one of the chapter of this book, Professor Malomet and Professor Vega, and also Professor Sergey Vladimir Dmitry. And if you want to get more information about the phi-4 and sine-Gordon model, we can refer to these two books. Let's start with the famous nonlinear Killing-Gordon model, which is the sine-Gordon model. The sine-Gordon model, in fact, is the integrable model, and it has a 1, 2, 3, or even 4 exact soliton solution, which you can see where you can see from this in this screen. The King solution are present in this form. In here, delta K is the Lorentz factor. And we have also the Breder solution and King and King anti-King solution of this model. In the right shapes, you can see the form of the King and anti-King and Breder of this model. I just want to attract your attention to the energy of the King and the Breder. Here, when you can see the energy of the Breder is approximately double of the energy of the King. We will back to this energy later in the few slides. Here, I just show the time evaluation of the King and anti-King. I think you cannot see the evaluation because I didn't make a full screen, but anyway, as you can see here, when the Kings and anti-King moves, they keep their velocity. The velocity cannot change. In the bottom shape, I have shown the standing Breder. Of course, if the Breder has a velocity, it can move to the left and to the right. There is a specific conserved quantity in this model, which is called the topological charge. The topological charge is always conserved during the interaction of the solitons. The topological charge can be defined by difference between the value of the field in plus infinity minus the value of the field in the minus infinity. If we subtract these two values, for the King we have the positive value, and for the anti-King we have negative value. In fact, if the topological charge is not equal to 0, we call the soliton topological soliton. If it is equal to the 0, we call them non-topological soliton. In fact, the origin of topological solitons the conservation, I mean the conservation of the topological solitons, topological charge is very different from the conservation of the other quantities. Topological charge are conserved because of the finiteness of the energy. Here you can see if two kings of the sine-Gordon model collide with each other, they can repel each other. I think, sorry, I guess you cannot see in this screen, but anyway, for king and anti-king, where they interact with each other, they attract. And but for the 5-4 model, the scenario is quite different. In fact, the scattering data depends on the initial velocity of the kings. For the initial velocity of the kings, if it is higher than the critical value, when the king and anti-king interact with each other, they escape to the infinity after the interaction. But if the initial velocity is below the critical value, we have quite chaotic behavior, which we have either the king and anti-king can form a bound state, or they can interact with each other with 2 or 3 or even more times, and then they escape to the infinity. In fact, such a behavior in the 5-4 models comes from the fact that a king in the 5-4 model has an internal vibrational mode. When they interact with each other, the internal mode can be excited. And if these two kings collide with each other, if the resonance happens, the solitons can get energy from the internal mode to the translational mode, and they can escape to the infinity. Here I have shown the final velocity and initial velocity of the king. As you can see in the right figure, the final velocity of the kings after the interaction as the initial velocity of the king. In some regions, we don't have any data here, which means that we have a bound state, and the number of collisions are shown with different colors. For example, the blue color shows for the case that when king and anti-king interact with each other with 2 times, and for the green color, they interact 3 times. King and anti-king can be formed. In fact, they have many applications. If we have a number of pendulum which are connected through the rope, when we hang them and we excite them, we can see that the king and anti-king and also king-king collision can be created in such a system. One of the interesting example of creation of king and anti-king is in the Buckel graphene, in which that Pershing and their co-authors shown that if we have a graphene and they have shown that if the graphene is relaxed in the direction along the trench and compressed in the transverse direction, the kink can be moved inside such a system. In fact, this moving kink can be created by pulling a group of atoms in the Z direction. Let's say that we have a graphene here like this, and if we compress the graphene that in the transverse direction, you can see that we have a kink. And if we pulling such a number of atoms in the minus Z direction for 10 picoseconds, the kink can be formed. Here you can see from the data from molecular dynamics, which are exactly fitted to the 5-4 kink. And in the right bottom figure, you will see that if we increase the force exerted by the atoms, with increasing the force, the velocity of the kink inside the graphene can be increased. And of course, there is a threshold value for this value. And you will see here in the next picture that if two kink and anti-kink in figure A, kink and anti-kink are created by 60 pico-newton per atom pulling by a force, and in figure B, they are created by 200 pico-newton per atoms. In figure A, they have a bound state, and in figure B, they collide with each other in the graphene and they escape to the infinity. But in the bottom figure, if we increase the force of the atoms up to 61 pico-newton per atom, we can create two bonds resonance here. Another example of the creation of the kink is that if we have one-dimensional nonlinear chain, if number of atoms, let's say that K, we call it number of atoms by K, if they move toward such a chain with initial velocity V0 and they collide with the change, the kink can be created in such a nonlinear chain if the interatomic potential would be in the form of the Morse potential and the on-site potential would be in the form of the periodic one. In fact, the minimum initial velocity that need to create the kink inside this change for one atom is very high compared to the 2 or 3 atoms. As you can see, the left figures, for one atom, the horizontal line shows the number of atoms, K is the number of atoms, and the vertical lines shows the minimum velocity of the atoms that can be collide with the chain. As you can see, kink by molecules are more efficient in the initiation of the mass transfer by kinks than the case of the single atom impact. In the right figure, you can see even we can create 2 kink in such a systems. Where in the top figure, the velocity of the kink after its interaction is shown, and the bottom figure shows the velocity of the second kink that can be created in the chain. One of the interesting behavior of the soliton is the interaction of the kinks or anti-kinks, or let's say that solitons with party-time symmetric defects. In fact, in 1998, Bender and co-authors they have shown that the non-Hermitian Hamiltonian can also have a real spectral under the parity-time symmetric conditions. After they shown such a behavior, a lot of studies shown that the parity-time symmetric is a good topic to study. In fact, here we want to show that the interaction of the solitons, kink and anti-kink, with such a petit symmetric perturbation. We want to send the soliton from both sides to the perturbation and to see what happened for the solitons. Here, I start with the very simple model, with the sine-Gordon model. We know the equation of motion for the sine-Gordon model. If we add the perturbation to the right side of the model, we can create the PT symmetric in this system. The shape of the perturbation are shown in the right figure. In the left side, we have the gain side, and in the right side, we have the loss side. We want to know if kink and brother moves toward this perturbation, what happened after the interaction? For numerical simulations, we introduced the mesh with number of 3000 atoms, and we discretized our equation of motion with Sturm methods. And for the lattice space, we use 0.1, and for the time space, we use 0.005. And we use absorbing boundary conditions in the borders to avoid the reflection of the small amplitude waves from the borders. One of the powerful analytical model which can be introduced is the collective variable model. In the collective variable model, we introduce one collective variable to the soliton field, and we put soliton fields into the Lagrangian and extract the equation of motion from the Lagrangian. In fact, by collective variable method, we can test the validity of our numerical simulation. For the sine order model, if we use such a model, because the sine order model does not have any internal vibrational load, we can introduce one degree of freedom, which is the position of the kink, and we can extract the equation of motion, as you can see in the screen. Here, I have shown the time evaluation of the kink during interaction with the PT symmetry defect. In the top figure, when the kinks come from the gain side, as you can see, it tracks, it first accelerated and then decelerated. But the final velocity of the kink after interaction is almost the same as the velocity before the interaction. The figure shows two different results for different initial values. The only effect of the kink with defect is the phase shift. As you can see, the phase shift from the figure. In the bottom figure, you will see that when the kinks come from the right or left side, from the gain side, the energy, the total energy of this system increases and then decreases. And after the interaction, the final velocity, the final energy is the same as the energy before the interaction. What happens if the kink comes from the last side? From the last side, we have two different scenarios. If the kink has enough velocity, it can pass through the perturbation. But for the velocity, for some initial velocity, it can be trapped in the perturbation. As you can see in the top figure, the kink comes from the last side. If we choose the amplitude of the perturbation 1.5, the kink doesn't have enough energy, and as a result, it's trapped in the defect. But for smaller amplitude, kink can pass through the perturbation. Kink critical velocity can also be found. As I told you in the last slide, there is a critical velocity for the interaction of the kink with the defect, above which kink can pass, but below which can trap by the defects. Here I show the result for the numerical and for the collective variable method. As you can see, if the amplitude of the defect increases, the initial velocity increases. The kink phase shift can also be found by during the interaction. We have calculated the kink phase shift from when the kink comes from the gain side and also from the last side. As you can see, the left figure shows that when we increase the initial value, the phase shift decreases in both cases, but in the right figure, for the initial velocity below some values, we don't have any phase shift because the kink can be trapped here. The interaction of the breather with PT symmetry defect is more interesting because the breathers has a frequency when it moves, and as I told you about the energy of the breather and kink, which I wrote them again here on the top, and as you can see, when the breathers come from the gain side of the defect, it can split into different to kink and anti-kink. The wavy lines show the breather and the straight line show the kink. Here I have shown different scenario for the different initial value of the breather. In fact, the initial position of the breather is the important parameter during the interactions. As you can see, for example, in figure B, if we change the initial velocity of the breather in figure B and figure F, the frequency decreases, but in figure C, the frequency of the breather increases after the interaction, which shows that the energy of the breather after the interaction can move during the interactions. And in figure A, D, and E, breather can split into kink and anti-kink. Here, I have shown the energy of each sub-kink by this consumption that the sub-kink of the breathers have the same energy. Here you will see that the energy of each sub-kink as an initial position of the breather in some regions that we can see that we have some loop. In those loops that breather can split into kink and anti-kink. The above figures show the case when the breather come from the gain side, and the below figures show the case when the breather come from the less side. In fact, such a behavior can be explained by the kinetic energy of the breather. We know that when the breather moves, kinetic energy of the breather have a sharp maximal and the interaction points. In fact, the position of the sharp maximal during the interaction is an important parameter. If the interaction happens in the gain side, as a result, breather can gain energy from the defects and it can split into the kink and anti-kink. As you can see from the red line after the interaction, the line cannot oscillate, but the dotted line, when the breather moves, it can touch both loss and gain sides, which means that the breather can lose and gain energy equally, and as a result, it cannot split into the kink and anti-kink. One of another example is that to consider the interaction of the 5-4 kink with the PT symmetric model. Let's see what happened if the kink in the 5-4 model collide with the PT symmetric defect. Here again, I can add the perturbation to the right side of the equation, and I introduce the defect in here in the bottom figure, as you can see. Here, when the kinks of the 5-4 model comes from the gain sides, a noticeable internal mode can be excited, as you can see from figure A and B. The figure shows the kinetic energy of the breather as a time. We know that if the kink get internal mode, its kinetic energy can oscillate with time. But if for the last side, you see the bottom figures, when the when the kink comes from the last side, we cannot see any excitation of the internal mode. But if we increase the velocity of the kink, excitation of the internal mode is noticeable, as you can see in figure B. When we increase the kink velocity, the excitation increases. Here, our collective result confirms this finding, which shows that the amplitude of the kink internal mode can be oscillates for the case when the kink comes from the gain side in figure A, but for the last side, we don't have any excitations. Another important things is the interaction of the 5,4,5,6 kink with the PT symmetric defects. In fact, here we found very interesting phenomena during the interaction kink with the PT symmetric defects. When in the 5,6 model, as you can see in the top figure, when the kink come from the gain side, interact with the PT symmetric, and during the interaction, it's produced some phonons, and phonons can be seen in the figure. But for some initial values of the kink in figure B, phonons can be amplified in the gain side of the defects, and interestingly, they can form kink and anti-kink after the interaction. As you see in the figure B, we have 3 kink after the interaction. But in figure C, the number of kink can even increases up to 5 numbers. You see it in the figure C, we have 5 kink after interaction, which shows that when the kinks come from the gain side, after the interaction, the number of solitons and anti-soliton increases after interaction, which is very interesting topic in this study. Here, I have shown the amplitude, the number of kink and anti-kink during interaction for different initial velocity and amplitude of the defect. As you will see that when we increase the velocity and amplitude, the number of kink and anti-kink created after interaction increases. Interestingly, for kink and anti-kink, they are not symmetric. We have different results for these two, kink and anti-kink. In fact, we have also observed such a behavior during the interaction, kink and anti-kink defect. If we send kink and anti-kink from both sides of the defect, when they collide together, we can see different scenario. For example, in figure C, again, 2 kinks come from both sides, but after the interaction, we have 4 kink, which means that the phonons are created inside the gain side and they change into the kink and anti-kink. In figure E, we can also see that the boson or barrier can be formed after interactions. Here, in fact, we introduced a machine, which such a machine produced number of soliton and anti-soliton. We sent one soliton from one side, and after the interaction, the soliton and anti-soliton, many soliton and anti-soliton can be created. This would be interesting topic for future investigation, and in fact, we can do it for other models. The interesting thing about this topic maybe would be even prominent for high energy physicists. We know that from the Big Bang theory that the universe began about 3 billion years ago. It proposed that the universe started as extremely small and dense point of the matter and energy, which then exploded and expanded rapidly and creating all the matter and energy that makes up the universe as we know it today. The question is, can we say that after the Big Bang, the universe was in the form of the PT symmetric, and a particle or antiparticle moves inside such a symmetric, and that is why we have such a number of particle and antiparticle around us. Who knows, maybe we had it. Now let's go to study the interaction, in fact, the high energy density in collision of n-kink and anti-kink. I have shown you that kink and anti-kink can be created in medium, in buccal graphene or in the nonlinear chains. Suppose that we have number of kink and anti-kink, they move toward each other and they collide together. And when they collide, the maximal energy density can be increased. And it is important to know what is the maximal value of energy density or extreme value of energy density during this interaction. This would be an interesting topic, especially for solid state physicists, because we know that if the interatomic bond increases, then the critical value, it can change the structure of the matter. Here I have to show you how the high energy density increases in the Sine-Gordon model. Let's calculate the high energy density and extreme value of this model in the Sine-Gordon model. For the Sine-Gordon model, we can easily write the energy density in this form, which you can plus the kinetic energy and the elastic strain energy and on-site potential energy. In fact, for energy density, we have two forms, kinetic energy and potential energy. But for the potential energy, we split it in two different terms. I call them elastic strain energy and on-site potential energy. And we want to know if number of kink and anti-kink collide together, what is the maximal value of each terms? I mean the kinetic energy, elastic strain, and on-site potential. I also introduced the elastic strain, which is the derivative of the field respect to the x. This can be positive for the tension and it can be negative for compression. And in order to get the kink and maximal value of the kink and anti-kink in the collision of the soliton, kink and anti-kink should arrange alternatively, which means that each kink or each anti-kink must have neighbors with opposite topological charge, because as I explained that the kink and anti-kink can attract each other, and in order to get the higher maximal value of energy density, they must arrange alternatively, as I shown in this figure. Let's start with the case of one. Let's say that we have one kink, and we can easily calculate the maximal value of the kink. We know the exact value of the kink for the Sine-Gordon model. The kinetic, if we calculate the kinetic energy, the kinetic energy will be zero. But it is better to say that here we calculate the maximal value of the kink and anti-kink for a slow solitons. Obviously, if we increase the velocity, this value depends on the velocity. But for us, it is interesting to know what is the result for slow moving kink and anti-kink. You see that for zero velocity kink, the kinetic energy is zero. The maximal value of elastic strain energy is 2, and for on-site potential is 2. we can calculate the maximal of elastic strain and minimal of elastic strain, which is 2 for the kink and -2 for the anti-kink. Here it can easily be seen that in this case, the total maximal energy density is equal to the sum of value of the kinetic and elastic strain and on-site potential. For 2 kink, the exact soliton, 2 soliton solution of the soliton model is known. Here we have a separatrix 2 soliton solution. This solution describes the kink and anti-kink that after the collision at t equals 0 move apart and the velocity vanish as infinity. In fact, we can calculate those maximal values for 2 kink collision because we have the exact value, and it is easy to calculate the exact value of these numbers. I have calculated them here. You will see for the 2 kink, the maximal energy density is 8, and the other numbers, as you can see here, the figure A shows the time evaluation of the kink. Two kink comes from together and they interact. You see in figure B, the maximal value increases to 8 at collision point, and the other results shows the other value of the terms. For the case of 3, n equal 3, the separatrix solution of the sine-Gauss model also exists. This solution describes the anti-kink standing at x equal to 0 and 2 kinks that after the collision with the anti-kink at t0 move apart and the velocity vanishes as t goes to 0. Here you will see the maximal value of the energy density is about 20, and we have also calculated the other values. And for the 4 kinks interaction of the 4 kink, although we have 4 exact soliton solution of the sine-Gauss model, but it is hard to calculate these value analytically. Therefore, we calculate them numerically. We send 4 kink and anti-kink toward each other with from different positions. As you see in figure 8, kink 2 and 3 move toward each other, and we play with the parameter of kink and anti-kink 1 and 4 in order to collide all the kinks and anti-kinks at one point. As you will see, the maximal value of the energy density here is 32. And the other values, as you will find them here. For the 5 kink, we can also do that. Here, the results, here I have calculated the result for the 5 kink collisions. And you see that after the interactions, we have 3 kink and 1 brother. And for the 6 kink, the maximal value increases to 72 in this collision. And the other values are shown in this slide. Here I have collected all the numbers. As you can see, maximal energy density is proportional to n squared, which n here is the number of the kink. If the number of kink is even, the maximal value energy density is n times n squared, but if the number are odd, this value is 2 times n squared plus 1. From this table, we note that the maximal value of kinetic energy increases rapidly with n for even and wide. For odd, n a rapid growth with n is observed for maximal value of elastic strain. As you can see, the on-site potential doesn't change during the interaction, but the tensile strain also increases. And if I want to conclude my talk, I would like to say that for the sine-Gordon model, we have considered the interaction of the kinks, and also for the 5-4 model, we have indicated that for the 5-4 model, the results crucially depends on the initial velocity of the soliton. And for the we have also shown that when the kink hits the PT symmetric defect from the gain side, a multiple soliton on this soliton can be created after the interaction, which is a very interesting topic for future investigation. And the extreme value of the elastic strain and energy also calculated during all the collision of the N kinks. And this can be happened when kink and anti-kink arrange alternatively. For future investigation, it is important to study the interaction of the 5-6. I mean, calculate the maximal value of the higher order field theories like 5-6, 5-10, and 5-12. For these models, kinks can have a long range tails, which would be interesting for future investigation. And on the last topic, since we have shown that when kink interact with the PT symmetry defect, some phonons can be excited. Interaction of the phonons with the kinks can be also interesting topic for the future investigation. Thank you very much for your attention. I think I need to end my talk here. Thank you.
Thank you very much, Daniel, for the very nice lectures. Are there any questions for Daniel?
Yeah, can I ask a question?
Yes, please, Professor Malumet, go ahead.
Yeah, hi, Daniel. Thank you for your talk. And the question is, actually, it's known that if you have kinks in non-integrable models, such as 5-4 or more complex models, kinks may have the internal mode, the shape mode.
Yes, yes.
So did you study systematically the excitation of the internal mode by the kink-anti-kink collision? So in the case of some non-integrable extension of the sine-Gordon model, this can be also studied, I guess, for the kink-kink collisions. Was it studied systematically?
You mean that the scattering of the kink with the PT symmetric defect, yeah?
No, not PT symmetric, just a simple model, but non-integrable when the kink may have the internal mode, so you can collide them two, for example, kink and anti-kink, where this internal mode is not excited, but as a result of the interaction, you will, in the outcome, you will have kink and anti-kink with excited, which carries the excited intrinsic internal mode. So did you study this possibility?
Yeah, actually, we didn't study that for the maximal values. No, we didn't study that, but we just studied them for the sine-Gordon model. Of course, if we want to investigate the effect of the internal mode, that can be also affect the result of the maximal energy density during the interaction.
Yes, of course.
You are talking about the wobbling thing, yeah?
Well, yes, it is called,
Yeah.
yes, exactly. When you have the excited internal mode, people call it wobbling kink, right?
Yeah. No, we didn't study that. But of course, that would be interesting topic for future investigation.
Okay, thank you.
Are there other questions for Daniel? Please, you're welcome to raise your hand if you're one of the attendees online, and I can immediately give you the right to ask the question in person. Or is there any comment from Professor Weigel? Sorry to put you on the spot.
Okay, not really a comment. I could have a number of questions, of course, but it's so.
Yeah,
for example,
you're welcome to ask.
Maybe it's easy to go over to the office and talk to Daniel in person. But one question I would, for example, you have your gain and loss in essentially just as a static source in the model. Is there any way of making it dynamical so that it, for example, would be something like a charge distribution of a charged particle that also has, well, some mass and has its own equation of motion?
So sorry, can you repeat your question again? I didn't get that.
Okay, so you have your gain and loss, which you're essentially modeled as two Gaussian functions, which are static and they are sitting in place.
Yes, yes.
Okay. Is there some way of making that dynamical in a sense that rather than having it like a dipole, it would be a dipole distribution of a real physical or let's say of a dynamical particle in there, so which has its own equation of motion and would then interact with the kinks?
Actually, for the perturbations, we just added the perturbation to the equation of motions, and we send the solitons from both sides of the models. And yeah, but for those questions, you mean that how do we calculate the main equations when we add the PT?
No, well, you could, for example, think that this gain and loss indeed is a dipole distribution associated with a real dynamical variable.
Yeah, yeah.
Okay, and that and for that dynamical variable, you would have its an additional coupled equation of motion.
Now you are talking about the 5-4 model in PT
well,
symmetry.
It would be no, it would be yeah, with the PT symmetry. So, but the question is, this additional interaction, can that somehow be made dynamical in a sense that it's really the charge distribution of an additional charged particle that interacts with the kinks?
Sorry, I cannot understand your
so
question. Maybe we
yeah,
can talk later.
Sorry. Yeah, okay.
Daniel, there is also a question in the chat, and the question reads: did any discrete nonlinear equation obey the kink soliton?
Did any discrete nonlinear?
Did any discrete nonlinear equation obey the kink soliton? That's the question in the chat.
Well, actually, this is depends on the form of the potential of the Lagrangians. For if, of course, we cannot say that for any potential of the Lagrangian, we may have a kink solution. If, let's say that we call the potential as a UFP, if UFP has a unique absolute minimal, there can be no static solitary waves. But if such a potential has a more than one minimal, we may have kink and anti-kink solutions.
Can I ask a short comment on this point?
Yeah.
Please.
Yeah, okay. So as concerns kinks in the discrete models, you have a neighbor who did some interesting work on this topic. Neighbor, I mean Professor Igor Barashenkov. He is a professor at the University of Cape Town.
Yeah.
I guess close to your place. And he in particular had some works in which he developed some discrete, specially designed discrete model, which is not integrable, but nevertheless, it admits some exceptional exact solutions for moving solitons, I guess moving kinks. This is actually the most non-trivial issue in this case, because to obtain a standing kink, which is essentially pinned to this discrete lattice, it's a relatively simple objective. But what is really difficult is to try to produce a kink which would be able to move in the discrete system, because if you just try to push it, it will move for some time, but it will eventually come to a halt because it will be losing energy because of the discreteness. And so Barashenkov and some other people, they developed some very special models in which some exceptional solitons can be moving in the discrete system as exact solutions at some special values of the velocity. So I guess they may be sort of kinks and anti-kinks, so they can move in either direction. So maybe you can actually try to look at some works of your neighbor.
Excellent. Thank you
Thank
very
you very
much
much for
for
coming.
those comments. And there is a question by Belobo, and I've just given Belobo the right to talk. So Belobo, please unmute yourself and ask.
Okay, thank you very much for the presentation. Did you hear me?
Yes,
Yes,
I can hear you.
Okay, thank you very much and for the nice presentation, nice talk. I listened and I want to understand what you mean by soliton machine. How does it work in reality? So you insert one soliton into your machine and it delivers many solitons. So it seems like the modulation instability mechanism. So my question is the following: do we know analytical expressions of solitons generated after the machine in such a way that you can make predictions, or we just have many solitons but we don't know how to make predictions with them? So we don't know, we don't have any actually we don't have any information of the analytical properties.
Yeah. Okay, thank you very much for your questions. Well, actually, we found these results very recently, which was published, let's say, 5 or 6 months ago. You know, there is no, as far as I know, there is no any analytical expression that can show this creation of soliton and anti-soliton during this meshing, which is something which is very important that I didn't mention here. These systems, let's say, let me show you here in this screen. When we add the PT symmetric perturbation to the equation of the motion, this system is non-conservative, which means that we've produced some energy in some specific position of space, and then we reduce this energy. And just keep in your mind that this system is not conservative, and probably that is why we can see here when the kink collide with the perturbation, it can be excited some phonons, and the phonons are trapped in the gain side. The gain side produce energy, it gives energy to the phonon, and phonon amplified, and it can be created soliton and anti-soliton. But I never seen any analytical expression, but there are some other professor here who can confirm me or not. Maybe Professor Malamet can say something, but I didn't say anything, any analytical expression. This is just numerically what I found in my results.
Okay, thank you.
You're welcome.
Thank you. Daniel, there is another question by Etienne. Etienne, you have the right to speak. You're welcome to make your comment or your question. Yeah.
Hello.
Hello.
Okay, great. I wish to start by thanking you, Daniel, for your nice presentation. And my question is, let's say, somehow twofold. The first point is about what you call soliton machine. How is your soliton machine different from the beam splitter as published by Humberto and colleagues?
Well, actually, I didn't see that paper. Maybe you can send me to that
okay.
paper.
Yeah, I will maybe check the link later to see the paper, and then I can send you. Sorry?
By meshing here, I just mean that PT symmetric perturbation. I mean, the term of the meshing here is the PT symmetric, and this is what I mean during my speaking.
Okay.
But on that paper that you mentioned, I don't have any information about that. Maybe you can just send me that
Yeah,
paper
it's
and
mostly
explain.
some kind of on-demand beam splitter, where you, let's say, you can send a beam, it can be a soliton, and then at the output, you have a certain number of solitons. Okay, yeah.
Is that in the form of the PT symmetric or?
I don't think that this is a specific case where we have PT symmetry. Okay.
I really have no idea about that paper.
Okay. Yeah, and this my second question then is about let's say the loss, the gain and the loss that you have within your system. The first point is, do you know how physically this can be realized? Do you have any idea?
You mean that of course, in some nonlinear Schrödinger equation, we have some application for this model, but in the nonlinear models, no, this is just theoretical model as I know.
Okay, this one thing, and then my last point is about what we call supercurrent. Can we, since we have, let's say, a system where in the middle you have gain and loss, which is like how am I going to say it, may be loss and pumping. So is there any kind of supercurrent flow that we can envision, let's say around this system with gain and loss at a time?
Sorry.
I want to know if there can be creation of supercurrents around this pair loss gain.
What do you mean by supercurrent?
Okay, let me see, explain it. So let me take the example of for instance a photon BC. A photon BC, I mean a Bose-Einstein condensate of photons. So in general, it is prepared in a medium where you have gain and loss at a time. Gain because photons are being pumped into the system, and at the same time you have loss because photons are being lost, let's say, ejected outside the system, let's say the cavity, we call it cavity. So in that case, there is some kind of supercurrent flow that we have, because I mean, due in general to the fact that you have not only a gain but also a loss in the system. And I'm just thinking if, okay, actually the trouble I had is that I mean, if you told me, for instance, which kind of physical realization we can have, then it could have been easier for me to really tell you that if it is in this system, this is what we can have. So this, for instance, the kind of system in which I see already this kind of thing happening. Although it is not directly modeled by the Psi-Gordon equation as you showed, but probably it can be the same stuff physically. I don't know.
Well, actually, I didn't again understand what is your question, because you're talking about Bose-Einstein condensations, and I really don't know what you mean. Sorry for that.
But, may I suggest, Daniel and Etienne, maybe you seem to know each other.
Yeah, maybe you can just
bring
find,
this
send me email. We can discuss more about that.
Also, I'm looking at the. Thank you very much, Etienne, for the question. Yeah. I saw before we bring the mini school to an ordered conclusion, I saw that there were a few requests in the chat for the issuing of certificates of attendance or something. any one of the participants needs one, please just email us and we will be very happy to do so. We don't do it by default because most people never request one. So if you need one for whatever reason, just drop us an email and we will do it without any problem. So then my last pleasant duty is to thank the team of the speakers of this very nice mini school. Professor Malamed is still with us. Thank you very much for joining us. Professor Weigel, thank you. And then there was also Professor Dmitriev, who is not with us this afternoon. So a big thank you to him as well. And of course, a big thank you to the last speaker, Daniel, for putting this all together and for concluding with a very interesting talk. Yeah, then thank you very much, everyone. Thank you very much for the participants.